Hello guys, welcome again. In this video, I'm going to explain how to write Verilog code for full adder in structural model. Let me give a brief recap of how full adder would be so that in remaining models, I no need to get back to this. So this is how full adder looks like. So this is the truth table of full adder, all possible 8 combinations. 0002 111. Now the expressions for sum and carry, if you write k map, so you'll get sum as a XOR b XOR c, and for carry you'll get ab plus bc plus ca or ac. Okay, and you also can design from this. This is used for instantiation, which I'm going to explain soon in the next coming videos. So this is using instantiation, so that you can look here, this red dotted part can be modeled as one half adder, and this another dotted part can be modeled as second half adder, and the total will be using full adder design can be done using two half adders. But for time being, let us not go to that. Let us strictly rely on this structural model, and this is how the carry expression would be. See, you're seeing like this red circled part, and for some we are going to use this. Okay, those things. Let me undo those two, but I think you know those things. Okay, now writing right away the code as I have already written here. Okay, now if you see here, I gave the module name as full underscore structural, because this is structural level of coding. And here itself I declared for a change, just for a change, here itself I declared, but here also you can write as input and output. Below this you can give like this input, all those things, but for a small change I written here. So sum and carry not are the outputs, and my inputs are a b c. Okay, now if you look here, the intermediate connections here, there is one intermediate connection here, and one more intermediate connection, this connection and these connections. So all these intermediate connections will be declared as wires. Okay, last, it's always preferred to write, it's always suggested to write these wire connections at last, so that you will know what are the wire connections that you are declaring. For time being, you assume that first XOR gate G1 I named it as. So the input of this XOR gate, directly I have given A, B, C. Okay, directly I have given A, B, C. That means I am writing directly the expression for sum here. The expression for sum I am writing directly as A XOR B XOR C. This term I am writing directly for sum, A XOR B XOR C. But for carry, as I am designing using this, instead of writing this bulky logic, I'm trying to optimize the circuit by designing here from itself. Now for this AND gate, you want this connection, which is the output of this XOR gate. So I am writing one more XOR gate, this XOR G2, where the inputs are A and B and my output is K. That means this is my K here. See, I am writing here, this is my K, this part. Now K and this C are given as input to this AND gate. So for AND gate, K and C are given as inputs. Okay, now one more thing, from this first AND gate, this is taken as T. Okay, and this is taken as one more T. So T1 and T2, these two are T1 and T2. Now for that AND gate, the inputs are A and B. Okay, for the final OR gate, these two, this T1 and T2, these T1 and T2 are given as inputs, and output is taken as carry out, C0. So as this is structural model, you should write the structure of the design that you are going to simulate or synthesize. So once again, you check with the diagram and you try to draw the diagram on your own, and you check here, this is for direct sum, and to get this carry out, these intermediate wires and all, I have written this 3 other gates. So this is how you can write a structural model for full adder. Let me write the test bench also, as I have already written. Let me show you. So if you add a new Verilog test fixture, then these things will be given directly. I explained about these things in the half adder structural model. You can refer those, why you are getting these dot notations, and why reg to these things, and why declaration to these. You can refer that. Now here in the test bench, you have to check all the possible input combinations. That is from 000 to 111, and this operator is called as concatenation operator, which means you will get all these bits combined as single thing. So concatenation of A, B, C, where A, B, C are individually declared as 0, 0, 0. So concatenation of these three will give me a 3-tick B 0, 0, 0. Now after each 2 nanoseconds, I am changing the things and testing all possible input combinations. And this $monitor is used to display the waveforms. Whenever these values change, it will be monitored and display you the values. and after 20 nanoseconds of time step or 20 time steps, which is 1 nanoseconds each in the time directive, you can see here it's 1 nanosecond. So after 20 nanoseconds, the this checking will be stopped and you will get back, you will return back to this window. So now let us check how the model would be. Let us verify whether it's true or not, the truth table is true or not for these values. You have to check the syntax. As I already checked the syntax, I am directly running the behavioral model. So I will get the waveforms here. Okay, here you can see all possible combinations. If 0 0 0, my sum and carry are 0. Let me check randomly here. If 0 0 1, my sum is 1 and carry is 0. So if all are ones, okay, if all are ones, my sum is 1 and carry is 1. You can check for any value here, all will satisfy. And this is how you can write a Verilog code for full adder using structural model. In the coming videos, I am going to explain you how to write Verilog code in for full adder in data flow as well as behavioral model. Then after completion of these two videos, then I am going to explain how to write full adder using half adder using instantiation. Thank you for watching. That's all for this video. See you in the next one.